Good evening. May the 4th be with you. I'm Neil Madden. I'm the author of API Security in Action, published by Manning at the end of last year. So this book covers all aspects of kind of API security, so how to secure your APIs running on the server. It goes through kind of basic kind of secure coding, and then kind of session cookies up to things like JSON Web Tokens and OAuth 2. And at the end, we kind of get into kind of microservice APIs and Kubernetes and things like Internet of Things APIs as well. But tonight I'm going to talk about something that isn't actually covered in this book explicitly, but a lot of the advice still applies to it. So if you follow the advice in the book, you'll also be in pretty good shape with regards to this vulnerability. And this is Spectre, which was a kind of it's not really one vulnerability; it's a kind of family of vulnerabilities that were discovered along with another similar vulnerability called Meltdown, discovered around kind of 2017 time and made public early 2018. And these are quite interesting vulnerabilities because they attack vulnerabilities in the hardware, in the CPU itself, that the hardware is running on. So in the case of Meltdown, that attacked something called out of order execution, which is a feature of CPUs that executes code slightly out of order from the order in which the instructions appear in the program. Now, Meltdown was quite serious because it allowed you to kind of cut through lots of layers of security and read operating system kernel memory. So it was pretty serious, and that in turn allowed you to read memory of potentially other processes. And because it was doing this at the hardware level, it was cutting through all the layers of security. So if you think like a modern application running, it's typically running on a server somewhere, maybe in the cloud. It's maybe probably these days running in something like Docker, a container environment with various kind of hardening applied to that. And then you've got that's running on the host operating system, where there's kind of permissions and various kinds of layers of security at that level. And then you might be running on a virtual machine and all this kind of layers of security. And then underneath all that, you've got this hardware running on your CPU. And these vulnerabilities are cutting through and exploiting vulnerabilities in the hardware, which means that all these layers kind of get bypassed. So Meltdown was pretty severe, but it was also relatively easy to patch, and there's now patches available for most operating systems that mitigate Meltdown. Spectre, on the other hand, is more, as I said, it's more of a kind of family of vulnerabilities rather than any one specific vulnerability. And so it was much harder to patch, and some variants of it have kind of been patched and mitigated, but others haven't really. And some of them are still kind of potentially exploitable now. And so in this talk, I'm going to talk a little bit tonight about Spectre, how it works, which is quite kind of low level. So I'll try and explain it in simplified terms to try and help people understand what's going on with Spectre and why it's a serious vulnerability, and what it means in terms of people developing web applications. So one of the interesting things about Spectre is it's not just a kind of low-level vulnerability that you exploit by running, low-level like C code directly on a machine, but you can actually exploit it through JavaScript running in a browser. So that makes it very dangerous because you can run JavaScript in a browser in a web page that exploits this Spectre vulnerability and dumps memory that you shouldn't be able to access, and so it kind of breaks some of these security boundaries in the browser. So I'll talk a little bit about how that works. I'll show you a little demo that the Chrome security team knocked together, showing a kind of exploit of Spectre within a browser. And then I'll go on and then talk about some of now the kind of dust has settled on these vulnerabilities. There's starting to emerge some best practices and things to do in terms of web development and in API development for the web to try and minimize the impact of a Spectre vulnerability on your web applications. So if I go first of all to this page, so Google have this nice page called leaky.page, and there they've put up a proof of concept kind of exploit for Spectre, and there's a whole series of pages you can work through here, which kind of to some extent explain how Spectre works, although you do need a bit of background knowledge already. And then they've got this, it kind of culminates with this working demo of an exploit of Spectre. So this is running in the latest Chrome. So on my Mac I've got the latest Chrome, so it's all patched and up to date, and yet when I run this, you can see what it's doing here. This kind of what's made to look like a hex dump here on the right is actually dumping the memory of the Chrome process that is running this web page. So if I run it here, hopefully it will work. It's sometimes a little bit fiddly. In fact, I installed a Chrome update just the other day, and it's actually become a little bit harder to exploit this now, I've noticed. So these blocks here should all be A's if it's been exploited properly, and you can see they're quite noisy. So I'll try and run it again and see if we can do it any better. But it was working quite well, but they've obviously made some changes in Chrome again, I think, which have perhaps made it harder to exploit again. Also, this demo was designed to run in Linux rather than Mac. So this is running on a Mac. So it's been kind of, in order to exploit Spectre, it's often you have to be quite specific to the particular CPU and the architecture of the machine you're running on. All right, so it's kind of done something. It's not as good as I've had it done before, but it's kind of working. So what you can see here, these zeros at the start, that's an array, a JavaScript array that was created in memory by the code that's exploiting this. So it creates this array full of zeros, and then it kind of uses Spectre to basically read beyond the end of that array and read memory beyond the end of that array, which is just the raw memory of the process running in the browser process. These AAAAA bits, which should all be A's, but it's obviously getting a bit more noisy because it's not able to exploit the vulnerability as well. These are other arrays that it puts in memory just so you can see some stuff. So these are other JavaScript arrays that have been filled with capital letter A, or 41 in hex. And in between them, we've got some other stuff, which is just how they happen to be laid out in memory. And then beyond them, we've also got other memory beyond the end of even that, up to quite a significant amount of memory that we've managed to dump from the browser process. And this is in JavaScript. So you can see that it's being able to break the memory safety of JavaScript and read memory of the browser that we shouldn't be able to read. And the impact of that is that potentially it means that JavaScript running in your browser can read stuff that the security model of the browser should prevent it from reading. So when you're running code within a browser, there's a security policy known as the same origin policy, which kind of says which JavaScript should have access to which other stuff running in the browser. So particularly, JavaScript should only generally have access to things that have been served from the same server that served that JavaScript, the same origin. and not from other domains or other websites. So in particular, if you make a request to another website to read some data, typically you might be allowed to make the request, but you'll be blocked in JavaScript from reading the response. And if you've done any work with cause allows you to kind of relax this and in certain cases allow that to succeed. But if you haven't enabled cause, then you'd expect that nobody could read your data and then be able to read the response, because that would break the security model of the web. If you've got an API that's returning potentially sensitive information based on a cookie, that's sent with the request, you don't want some other site to be able to make that call to your API and get back that data and read it. And so browsers will typically block that from occurring. But if you've got a vulnerability like Spectre that you exploit, then potentially an attacker can load that data back into the browser. The browser will stop it being able to read it, but then it can run this Spectre exploit to dump the memory and read the stuff anyway. So Spectre is potentially really quite serious. And you can see that it's, this proof of concept is running in a modern patched Chrome on an up-to-date operating system. All right, so that's the kind of the impact of Spectre and why it's so problematic. And if you think as well, it's not just the data on the page, but potentially within this browser process as well, you've got things like cookies, tokens in local storage and things like this, credentials that can then be used to go and access other stuff. So you don't want those to leak either. So in terms of how it actually works, I'll tell you a little bit about how Spectre works in a kind of simplified way. When I was kind of initially getting into computers when I was young, I'm going to age myself here now, but they were a ZX Spectrum was my first computer at the end of the kind of 1980s. And CPUs then were really relatively simple and quite easy to understand, even for somebody just approaching their teens. Whereas now, obviously, they're completely different and much more complicated and much more sophisticated. And they have a lot of features now that are designed to improve performance. And Spectre and Meltdown kind of exploit some of the complex interactions between these features. So in particular, in the kind of 1970s and maybe in the 80s, although I'm not sure how true it was even then, the time it took to execute a CPU instruction wasn't that different to the time it takes to go out to main memory and retrieve some data from memory. So those things, took about the kind of same length of time, which meant that your CPU could be quite slow. So if it was executing this code, for instance, and it came to this if statement, obviously compiled down to machine language, and it needs to go and fetch this array length from memory, that's fine. It would just stop and wait for that to go off and fetch it from memory. But if you think about CPUs now, CPUs have got hugely faster over the intervening decades, whereas going out to main memory is still relatively slow. That has also got faster, but nowhere near at the same rate as CPUs. So accessing main memory now is now orders of magnitude slower than executing some CPU instructions. And so CPUs do a lot of tricks to kind of hide that delay. So first of all, they have a lot of caches on board now. So when you go and access some data in memory, it will load it first into a cache on the CPU. And then, if it needs to access it again, which it probably will do, it can just access it from the cache, which is much, much faster than having to go out onto the kind of memory bus and access this other chips for the memory. So that's one thing. And there's kind of multiple layers of caches and this kind of cache hierarchy. But the other things it's done is it's done lots of tricks now to kind of even and to kind of reduce the apparent delay. And one of the tricks it does is something called speculative execution. This is where Spectre gets its name. It's based on the speculative execution, which is a little bit like running a database transaction. And in particular, the one we're going to look at here is based on something called branch prediction. So if you've got this if statement here, and it's going to access this array, but before it accesses it, it's going to check that the index you're trying to access is less than the array length. So it's going to do a bounds check. And this might be in your code, or it might be in, if you're using Java or JavaScript, they do these checks automatically. They automatically check that the index you're trying to access is within the bounds of the array, so that you can't just read some memory beyond the end of the array, which was a common source of bugs in languages like C or C++. But either way, there's this if statement, and it's going to have to check this array length, and then based on whether that's either true or false, it's either going to execute this code or it's going to come down and execute this code. So these are the two branches. And because this array length might not be in cache, it might have to go out to main memory to fetch that, to be able to work out whether this is going to be true or false. And that's going to take a long time. So while it's waiting for that to happen, rather than sitting there and doing nothing, what the CPU does is it guesses which way it's going to go. And it guesses based on, say if this was in a for loop, or it's a function that's been called multiple times, it keeps track of what happened last time it was here. And so if, the last 2 or 3 times we've gone to this if statement, this has been true, then it's going to guess that we're going to end up in this then block rather than the else block. And so it will start what's called speculatively executing the instructions in here, which is, like I said, it's a bit like a database transaction. It starts executing them, but it doesn't make the effects of those instructions kind of visible just yet. It kind of buffers up the results of those instructions in memory. And then when this array length comes back from memory and it can work out this whether this condition is true or false, it then knows whether it got it right and whether this speculatively executed code was supposed to have happened or not. And if this was true and it guessed correctly, then it kind of commits that speculative execution and carries on as if this had just taken no time at all, basically. So it's won a lot of time by doing that. And potentially it could execute hundreds of instructions speculatively. So it's a huge time saving. But if it gets it wrong, and it turns out that this index wasn't less than the array length, then it rolls back everything that it's done, and it comes back to here, and then it jumps into this else branch instead. So it throws away all the work it did in here, which is exactly like kind of rolling back a database transaction. And the idea is that that's supposed to completely undo all the effects. So the fact, we've got an 8-byte array here, but I'm trying to access index 100, which is well beyond the end of that. But it might speculatively access that, and it updates this sum variable based on what's in element 100, which is actually just some random bit of memory beyond the end of the array that we shouldn't be able to access. But because it's going to just undo all of that, we shouldn't be able to see any of that, so it won't matter. At least that was the theory, that it shouldn't matter because we'll never actually see the result of that, so we can't do anything with it. So this is what Spectre proved to be false, basically, and it proved to be false because of the caches that I mentioned before. So when this gets undone, it undoes all of the effects of this data, but it doesn't undo any changes that were made to the cache. And so if this wasn't in cache before, and it gets speculatively executed, then it might be brought into the cache. And then we might be able to see then afterwards, by measuring very fine level, we can measure how long it takes to access different array elements. We can work out which bit got brought into the cache. And the way we do that is we create a new array, which we'll call our probe array. And this will have 256 elements, one for each possible element in a byte, each possible value of a byte, multiplied by some kind of factor that spreads them out a bit. So this 512 or 4096, I think, is used in the original paper. And the reason for this is a little bit technical, and I'll maybe talk about it in a minute as to why we're kind of spreading these out. But what we do here is rather than using our array element directly, we're going to multiplied by 4096. We're going to index into our probe array based on the value of our other array, the value that we look up in here. So this is this out of bounds read. So we're going to look at some value at index 100 that is far beyond the end of our array. And whatever byte is there is going to come back, and then we're going to use that to index into our probe array. Now I have to, because this is Java, I actually have to do a little extra trick here, because Java bytes are between minus 128 and 127. So I have to add this mask to make it a value between 0 and 256, so that that's actually a valid index into my array. But you can ignore that detail. So we're going to get back some value here. So let's say, at index 100, beyond the end of this 8-byte array, say there's the value 42 in memory, right? Although that is the values I've put in here. But say there's a value 52, for instance. Then this is going to come back as 52, get multiplied by 4k, and we're going to access that part of this probe array. So what we can do is we can arrange, before we run this code, we can arrange to flush this entire probe array from the cache to make sure none of it's in the cache. And there's various ways you can do that, which I won't go into. They're very specific to a particular environment. And then we're going to access this, and we're going to also flush this array length out of the cache, but not the array contents. So what's going to happen is the code's going to come down here. It's going to go, I've got to go off to main memory to get this array length. So while I'm doing that, I'm going to speculatively execute this, and I'm going to access this out of bounds value in this array and use the value of that to index into this probe array and add that to the sum. But then I'm going to undo it all afterwards because this turns out to be out of bounds. But now behind here, I can now write some code that looks like the following. And what it's going to do is it's going to use a high precision timer. In this case, I'm writing Java code, so I'm going to use system.nanotime. If you're in JavaScript, there's a bunch of, there were a bunch of high precision timers. So there's something called performance.now, which used to exist and sort of still exists, but was removed after Spectre, and I'll talk about that in a minute. So what I'm going to do is I'm just going to access my probe array at this element, and I'm just going to do, sum plus equals probe array again, multiplied by 4096. And so I'm timing how long it takes to access each element of the array, or each 4 kilobyte spread out element of the array, depending on what the value of the byte is. And one of these is going to be much faster than the others. So if n minus start is less than, some threshold value, that will tell me that that element of the array was in the cache rather than in memory, because accessing stuff from the cache is much faster than going to memory. And the only reason it would be in the cache was because it was cached here when we speculatively executed this code. And that tells me what the value of this array, out of bounds array index was, because it will be the same value of I here that's then caused this to be faster. So that is the trick that Spectre exploits. So we come down here, the CPU speculatively executes this code, it accesses some data out of bounds of the array beyond the end of our array, which is just an array in our language like in JavaScript. It then uses that to index into some other array which causes that part of that array to be cached. It then undoes everything apart from the cache, and then we can use high precision timers down here to work out which element was cached. And that's how Spectre works. And that's the kind of how we end up then dumping all this memory. Now, it's actually a lot more complicated than that. You can go and look at the code that Google Security on GitHub, so Google Security Research Proof of Concepts, and there's this leaky page thing. It's linked from the leaky page site. And you can see all of the details that they have to put into a real world exploit of this. And they had to go through a lot of kind of stages of building a proof of concept in C, and then slowly replacing parts of it with browser features in the browser, and eventually coming up with this JavaScript thing. And as you can see on mine, it used to work perfectly here. I've updated Chrome, and it's now not working quite so well on my Mac. I don't know how well it still works on Linux. Be worth giving it a try. But there's lots of these details. They're not reading individual bytes. They actually read individual bits, and they kind of repeat it multiple times to kind of reduce the noise. And there's a bunch of other stuff they have to do. So you have to kind of evict this array length from memory while not evicting any of the actual array contents from memory. So there's lots of these things you have to do. And every time you read something, you have to set up the cache carefully every time, just to make a single read of a single bit. So it's quite complicated, but you still get to read 128 bytes in a second. That's quite slow actually. So yeah, this is slowed down. Yeah, 300 milliseconds was what I was getting before. So I think it's having to repeat things multiple times now to try and average out the noise. So that's the kind of impact of Spectre, and that's how it works. In terms of the mitigations, then obviously when Spectre came out, browser vendors kind of rushed to kind of plug these holes, and there were various operating system patches that fixed Meltdown, as I said, and fixed some of the variants of Spectre. And then browsers made a lot of changes as well to try and make Spectre harder to exploit. So as I said, they removed these high resolution timers like performance.now, leaving only the kind of millisecond precision timers like new date and things like that. Because a millisecond is not the difference between accessing data in a cache and accessing data from main memory is usually less than a millisecond. It's hundreds of microseconds. So you need a higher resolution timer than that to be able to tell the difference. So they removed that timer, but that's not the only way you can create a high resolution timer in JavaScript. There's this nice web page called XS Leaks, cross-site leaks, which documents lots of different ways that you can leak information across browser security boundaries using features of the web. And they've got this nice page here on clocks and how to construct high resolution clocks from various other features. So one of the things people did was there was this thing called shared array buffer. And you can create a web worker, which is, kind of a separate thread that's running on its own. And you can have this shared array buffer. And one thread is just constantly incrementing a counter in this shared array buffer. And the other one can read it and use it like a clock, basically. So even though there's no explicit clock available, you can use this other thread, basically just incrementing a counter in a buffer as if it was a clock. And that can provide a sufficient high grain clock to be able to exploit this. So again, shared array buffers were removed from browsers at the time and disabled, so you couldn't use them. They've now sort of come back, some of these features. There are certain conditions that if you fulfill, you can start accessing these features again, but you kind of have to opt into more strict kind of what's called cross-origin isolation. So the other thing they did, in the original Chrome sandbox model, they had each tab in your browser in Chrome here ran in a separate process, a separate operating system process. And so everything within that tab was in the same process, and stuff that was in a different tab was in a different operating system process. And Spectre, the way Spectre works, it can't read data outside of a particular process boundary. So within a process, Spectre can potentially dump all of the memory, but it can't go beyond that process and start reading data from a different process. This is unlike Meltdown, which could break those boundaries down, but Spectre can't. But still, a tab is potentially, lots of different stuff in there. People build websites, they embed resources from other websites, images and things all the time. They call out to APIs from other websites, and potentially they embed other websites in iframes. And so this potentially was still a problem, because if you went to some malicious website and it embedded your online banking website in an iframe, if you're logged in because of a cookie, it's going to render your online banking website in this iframe, potentially showing your recent transactions and bank balance and things like this. Now, in the security model of the web, that shouldn't be a problem, because that embedded iframe, the parent page that's loaded it, can't access any of the data in that iframe, because the same origin policy prevents that. But if you think about it in terms of Spectre now, that breaks down, and the parent page could then run a Spectre attack and dump the memory of the entire tab process, including all of your transactions and things like that. So it potentially breaks this. So Chrome has moved now to a model they call site isolation, where it's not just individual tabs that have separate processes, but individual websites within a tab. So your online banking being loaded into this iframe is going to run in a completely separate process to the parent page that's trying to embed it. So even if that parent page tries to run a Spectre attack, it's not going to see any of the memory of that online banking iframe. So that's one thing Chrome did. Firefox are following suit with that. They're kind of gradually rolling this out. And I think Safari have done similar things. Safari also did some nice little kind of low-level things I was reading about. So one of the things they do is, rather than just always just doing a comparison for this array length, they would put in a mask as well. So this array length is 8. So whenever you access this index, they'd mask it by 7. So that what this does is it forces, without doing a branch, without doing any kind of branch here, this masking here forces index to always be between 0 and 7, which is all you can have for an array of length 8. And so it means that even if you try and speculatively execute, you can never read actually beyond the end of the array, because the code is going to restrict that index to within that. This works only if the array is a power of 2, so 1, 2, 4, 8, 16, 32, so on. If it's not, then what Safari does is it kind of rounds up to the nearest power of 2 and takes away 1 and uses that as the mask. But if you think that works quite well for small arrays, but if you think you've got a really large array, 16 kilobytes or more or something, then potentially the next power of 2 might be quite a way up, so it can still potentially read quite a way beyond the end of the thing. But there's been various kind of little tricks and things like that done. But none of them are entirely completely effective. Site isolation is pretty close. But there are still potentially some issues. And so now we're kind of seeing a lot of guidance now on how to deal with Spectre. I should say as well, these mitigations, so site isolation in Chrome, that applies to kind of desktop Chrome, and it applies to Android Chrome if you've got enough memory. I think it's 2 gigabytes of RAM. Otherwise, you're still using the old model. So there's still potentially a lot of browsers out there that don't have these mitigations enabled, particularly kind of low-end hardware, because the overhead of these extra processes adds a lot of memory impact as well. So if you've seen your memory increase footprint of Chrome rising dramatically, this is probably one of the reasons. So don't just blame Chrome developers. So what's happening now is the browser vendors are kind of coming together and starting to bring out guidance. So Google are kind of taking the lead here a little bit, and some of the other browser vendors is also bringing out their own guidance. So we've had blogs from the Apple Safari security team as well, and trying to bring together kind of best practices for web developers to try and avoid being affected by Spectre, or try and limit being affected by Spectre. And there's a nice TLDR. So this is a nice draft that was introduced in March, still being actively worked on at the W3C, which is kind of giving guidance for post-Spectre web development. So things you should do to limit your exposure to Spectre in web development. And the TLDR here is your data must not unexpectedly enter an attacker's process. So it's providing ways that you can limit your resources where they can be loaded so that they don't end up being exposed, being dragged into an attacker process. If we look at the security model of Chrome, so this is taken from a Project Zero blog post, not specifically talking about Spectre, but it's got this nice diagram here of the browser process. So now we've got all these different renderer processes that are rendering. They used to render individual tabs. Now they're potentially rendering a site within a tab. So all the stuff from a particular site. And you've got different ones for different sites or different ones for different tabs. And then you've got some other processes that do things like networking, graphics card stuff, and then kind of coordination processes and stuff. And so the idea is your site is running in here and the attacker's site is running in here. You don't want any of your data to end up in their process, because as soon as it does, they can potentially use Spectre to find out that data and break some of the security boundaries that you'd expect to exist in the security model of the web. So there's a bunch of stuff that you can do, some of which is in this book, as I said, because it's general security mechanisms that also have an impact on the exploitability of Spectre. And so they're things that you should be doing anyway for other reasons that happen to also have a good impact on Spectre. And then there's a bunch of new stuff that's being added that is kind of more Spectre specific, that allows you to lock down things a bit more. So in particular, I think the new stuff that's being added is kind of plugging a hole in the same origin policy. So the same origin policy should prevent these kind of attacks, but it has various kind of get out clauses. And in particular, so often requests are allowed to be made, but the calling process is just prevented from reading the result. So if you think about like a GET request, are generally considered to be safe. So you can make a GET request to another website, but you're blocked from reading the response unless you're in the same origin. But that could still be a problem, because if you think about a GET request from this request, it's going out, it's loading some resource which is coming back into here, and then at that point the browser's saying no, you can't read it. Well, at that point it's too late, because it's already in this process, and so the attacker can then run the Spectre exploit and read it anyway. And so these new facilities being added by browsers, new headers and things, are designed to stop data ever entering that process. So there's a bunch of things you can do. So one of the interesting things for me, so if you think about cookies and other kind of forms of credentials that are sitting in your browser process. Now there's things like if you are using local storage is specific to an origin already. So that will be stored within the process for your site. So now we have site isolation then that should be kept separate and won't be mixed up. But if you're using an older browser or one of these low-end browsers that doesn't have site isolation available or implemented, then potentially, local storage is vulnerable because it will end up in the same process for your tab as potentially as the attacker's code, and they can maybe then dump that from memory. So local storage is kind of maybe sometimes safe, maybe sometimes not. Cookies can be potentially slightly better here than local storage, which is going to add to the endless debate about whether local storage or cookies are better. I think we're shifting now back towards thinking cookies are better. And the reason for that is that cookie attributes, security attributes, actually help a little bit against Spectre. So particularly you can mark a cookie as HTTP only. And what that traditionally was used for was to prevent cross-site scripting attacks. So if you mark a cookie as HTTP only, it's not available to JavaScript. So normally a cookie, which is set by the server, can be read from JavaScript through the document.cookie variable, which means it's available in here in these renderer processes. But if you mark it as HTTP only, it's not made available to JavaScript, and the browser itself will send it on requests back to that same website, but it won't expose it to JavaScript. And the idea behind this was that, if somebody manages to run some JavaScript through a cross-site scripting attack in your website, then at least they can't steal your cookies, which was semi-effective because they can instead just make network requests from your code, and the browser will attach cookies anyway. But it is quite effective against Spectre because if you think about a cookie comes in here, so a response from a request comes in here to this network process, and it's got a set cookie header on it, which is going to set a cookie. And because it's HTTP only, it knows that it never has to expose it to these renderer processes, so it can just store it somewhere, I think either in this network process or somewhere down here. I'm not sure where they get stored. But it only goes there, and it doesn't go into the renderer process where the JavaScript is running, because it's never going to be accessible to JavaScript. And then so if that JavaScript makes a request, then that will come back through here and back through the networking process again, and the networking process can add the cookie onto the request. But it's never available in here, which has the nice side effect that it also means it's never vulnerable to a Spectre attack in here, because the JavaScript running in here runs a Spectre attack and can read this whole process memory, but the cookie is never there. So that's quite nice. But potentially there are still some vulnerabilities. So if you think about traditional anti-CSRF tokens, so CSRF tokens, so if you're adding random tokens to your forms to prevent CSRF attacks, then potentially those are going to be in the DOM, and so in this renderer process, and they can potentially still be stolen by Spectre. And so again, this is one of the motivations for the development of same-site cookies now, which again are covered in the book, which are a kind of the browser's own attempt to prevent CSRF attacks against cookies by making sure that cookies are only sent on requests that originate from the same site that the cookie is intended for, so attackers can't make these requests. So if you combine HTTP only and same-site cookies, I would still probably also continue using your anti-CSRF tokens as well, if you're using those, because there are some gaps in same-site, which I won't go into here. But the combination of those attributes makes your cookies pretty safe then from Spectre attacks. So that's kind of one thing. And I believe that works. So the HTTP only thing, I think that works in certainly in Chrome and Safari. I think it also works in Firefox as well. So the other things you can do then is you can add a bunch of security headers to your responses that limit your exposure to Spectre. So I said before about the idea of somebody loading your internet banking into an iframe within another page. And most internet banking websites will prevent this already because there's various attacks that you can carry out if your site can be loaded into an iframe. So there's things like clickjacking and stuff like that you can Google. And so in order to prevent that, there's a bunch of security headers that are kind of set. And one of these is this X-frame options header, which is very common to kind of set. You can set it to deny, or you can set it to same origin. And if you set this on your responses, then it means that they can't be loaded into an iframe. The browser will prevent that from happening. Or they can only be, if you set it to same origin, then it can only be loaded from this into an iframe from the same site that it's, or the same origin, in fact, that it's from. I won't get into the difference between origin and site in this talk. So that prevents that. There's also a newer version. So there's now, probably if you're doing any recent web development, you'll come across content security policy, which is the kind of Swiss Army knife of modern security headers. So that has a modern replacement in this frame ancestors directive down here, which is a kind of more controlled version of X-frame options. So you can say frame ancestors none, or you can list particular origins that are allowed to load your code into an iframe. This is actually from the book. This is code from the book for a REST API response. So there's never any reason to load a REST, a JSON response, say, into an iframe, because it's not HTML. It's not ever active content. So you can set a content security policy which turns off frame ancestors, and also adds this sandbox attribute, which means that if an attacker somehow managed to get the browser to think that your JSON response was HTML or something, then it might execute and have unintended effects, and it might end up in the process, in the rendering process of an attacker, where they might be able to access the data that they shouldn't do. So you can have this sandbox attribute, again, just adds another layer of defense against this. So one of the other things you should always do is you should always make sure that you set the content type header correctly on responses. And you should always set this thing called X content type options header to the value no sniff, NOSNIFF. And what this does is it ensures that the browser knows what type of data you're returning, and it doesn't try and second guess that. So, in the old days, there was a lot of, and I think still now, there's a lot of resources that are served on the web that have incorrect content types on them. So browsers try and second guess sometimes by looking at what the actual data is, guess what the real content type is. And so by using this no sniff option here, you can turn that off and tell the browser, I know what I'm doing. This is JSON. It's never going to be anything other than JSON data. So don't try and ever treat it as something else. And the reason that's important is because even though this is a REST API returning JSON data, an attacker might try and set it as the target for an image tag, say, for instance, in their website. And that means, image tags are allowed to load data cross site. The browser's not going to block that because that's an essential part of the web, being able to embed images from different sites. And so what might happen if you're not setting the correct content type, then what might happen is that the browser goes off from the attacker's process. It goes and hits the network, loads your REST API using whatever cookies you've got for that user, get some confidential data back, and it's going to come back into this rendering process where the browser is going to look at it and say, well, that's not actually an image. It's not any kind of valid image format, so I'm going to throw that away. But at that point, it's potentially too late because it's entered into that process address space again. So it's potentially already, at the point the browser's throwing it away, it's potentially already there and vulnerable to this Spectre attack, where the browser can the attacker can use Spectre to read that value. So by setting a correct content type option, then the browsers can do something that they call cross-origin read blocking, which is a bit of or CORB, which is a bit of a mouthful. There are a few of these now, I'm afraid. And what that means is when it comes back, it's going to come in here into the networking process. The networking process is going to say, well, you wanted an image, but that says it's content type application JSON. And I know that that's the correct content type, and that's never going to be an image. So I'm going to throw it away here at this point. And so that data never makes its way into this renderer process again. So that's really important. That's one of the, there's a nice TLDR section here, 1.2 in this draft. So if you Google post Spectre web development, if I could talk, then you'll find this draft, and it is just a draft. So this is evolving advice at the moment, but it's got a nice section here which kind of summarizes some of the things. So I've talked about X-frame options. And I've talked about cross-origin read blocking just now. So this kind of prevents your data getting into the attacker's process, which is what you want to do. One of the other things they recommend as well is that you look at the headers on the request and decide, up front whether you want to serve a resource to where this has come from. So the origin header will be set to the origin of the JavaScript that's accessing your resource. So you can look at that. They also now set these secfetch headers, so things like secfetch mode, I think it is, which tell you how the resource was requested. So is it an image tag that's being loaded from HTML? Is it JavaScript calling the fetch API directly, for example, to load your resource? And what mode did they use? Was it a CORS request or not? And so on. And so those kind of tell you, how this is being requested, and you can look at those and potentially block requests that you think are dodgy. So I think that's the basic headers. Yeah, that's the main ones covered. So there's some new headers as well they're adding. So normally for a lot of resources, if you wanted to share them across origin, if you think about APIs and things like that, then normally you'd have to enable CORS, cross-origin resource sharing. But as I've said, there may be ways. CORS only applies to requests that trigger CORS protections. And that is what's called non-simple requests. So things like if you make a fetch API request from JavaScript with a non-standard header in it, for instance, then that will trigger CORS. But there's other requests that won't trigger CORS, which are basically anything you could make from HTML itself generally doesn't trigger CORS. So things like loading an image, that doesn't trigger CORS because it's a simple GET request. Submitting a basic HTML form doesn't trigger CORS, which often catches people out. So the browser will happily make a post request using just basic form data across sites and various things like that, but it just won't let you read the response. But again, there's potentially this issue of things getting into the attacker's process address space where they can then use Spectre to access it. For things that do trigger CORS, then obviously you can just use CORS to say whether that should be allowed or not. I won't go into CORS. CORS, again, covered in the book. But for things that don't trigger CORS, so things like loading something in an image tag, they've added these new headers that allow you to say whether you want this to be able to be accessed cross-origin. So there is the cross-origin resource policy header, which you can return on results, where you can say whether your resource can be loaded by pages that come from the same origin. That's the most restricted one. Pages that come from the same site, so potentially a subdomain of your site, or cross-origin, which means that anyone can load it. So to do that, you can add this response.header. something like cross-origin resource policy, same site, or same origin, say. That's the most restrictive one. So on API requests, that's probably what you should add if you're going to add this at all. And that says that only the exact same origin I'm from can load this unless it's allowed by CORS. There's also another one which is cross-origin opener policy. So we had CORB before, and I think this is same origin again. This is slightly different ones. So we had CORB, which was cross-origin read blocking. We now got cross-origin resource policy, or CORP, and the cross-origin opener policy, or COOP. And there's a bunch of labels you can apply to it. So this says who is allowed to open your page in a new pop-up window, basically. And the reason that's important is because when you open a page in a pop-up window, you get a handle back that you can use for post message and things like that. And so potentially it's similar to opening an iframe. So those are the basic kind of things you can do. I think the browser vendors would like you to start setting cross-origin resource policy on everything. So if you've got public assets and things that are supposed to be accessible by anyone, then if you start setting this cross-origin resource policy to cross-origin, which kind of opts in and says, anyone can access this. There's also a thing called cross-origin embedder policy, which I think is a bit more flux at the moment, which allows you to say, you can opt in and say that I am only going to load other resources that have a cross-origin resource policy that allows me to. So at the moment, potentially you can load other assets that don't set the cross-origin resource policy header. But you can opt into this mode where you require that header on all your resources. So the browser has an idea then that everything you're including in your site has been explicitly allowed to be included by other sites. And it means that anything that ends up in your render address space has been explicitly allowed to be in that address space. And then if you do those things, then the browser, or Chrome at least, starts enabling some of these features that they turned off before, so high resolution timers and things like that. And there's a kind of growing list of features now that are only available when you've got these things enabled. And that's because then you can guarantee that everything that's in your address space of your site said it was okay to be there. And so if you run a Spectre attack, anything that you're going to gain access to is only stuff that you've been explicitly allowed access to anyway. So we've kind of come to the end of the hour now. That's pretty much covered. I think I pretty much covered everything I was going to say on this. So to kind of recap, we've kind of gone through Spectre, what it is, why it's so severe. We've shown that it's still something that you can potentially exploit in browsers, although it may be becoming harder. The impact is pretty devastating when you can exploit it, because you can access a lot of memory that should otherwise be blocked by the browser same origin policy. But there's a bunch of nice things you can do then to reduce the impact. So using things like HTTP only cookies keeps them out of the process, adding these things like correct content type onto your responses, using X-frame options to prevent being embedded in a frame, and then some of these new things like CORB and CORP and COOP, and what's cross-origin embedder policy, COEP. So all of these new acronyms that hopefully are a little bit more less confusing to you now. There's a nice website that Chrome put together called web.dev, and they have, if you go into the Learn section and go into the security section, they have a whole bunch of articles around this stuff, so you can prevent info leaks. And down here you can see about these COOP and COEP and cross-origin isolation and things like that. So you can get a lot more information. Hope you enjoyed that. Buy my book. And if you have any questions, you can find me on Twitter and at Neil Madden. And happy to talk some more, because this is a fascinating, evolving area. All right. Thanks, guys.